Okay. Good afternoon, guys. So my name is Naveen. I'm from Mecademic, and I'm here to give a presentation on the precise part picking and the best practices and stuff. So I'm from Mecademic, and we are a Canadian manufacturer of high-precision robotics. So essentially, we do the same thing as what Fanuc, ABB, and they have been doing. It's just that we are defining a new category of robots, so with a compact footprint and high precision. So our flagship robot is a Mecha 500, and we also have another Scara that is coming out quite soon. So what we decided to do differently compared to other legacy manufacturers, obviously the size, but also the changed approach to robotics. So we have a robot with an embedded foot controller. So it handles all the kinematics and the motion control. So we are taking out the black box approach, having a proprietary software, a proprietary language. Instead, we have the controller that handles the kinematics and the motion control, and we leave the logic to the machine controller. It could be a PC or PLC. So it gives a lot of flexibility for our customers in applications like in med device, in other industries as well. The Scara is sharing the same DNA. So both robots, they have been built from the scratch. So we do everything in-house. So we do the CNC machining of the aluminum. So we use our own drives. We design and develop and assemble them in-house over here in Montreal. So we have been working with a lot of our customers in different industries. We started with electronics, started with testing of the devices, inspection, those kind of things, and med device as well. So think about all the micro assembly applications, pick and place of really small parts, those kind of things. So we have customers like Mechatronic and Boston Scientific in this region, and also in lab automation. So we are doing a lot of microplate handling, pipetting, liquid handling, and sample handling, those kind of processes as well. And in aerospace, so SpaceX is one of our good customers. So we are involved in the Starlink satellite projects, and we have automotive like Continental using it for say, multi-part assemblies, and also in laser, Coherent, and other laser manufacturers. So these are really complicated process where they need real high precision. So it's not just picking up small parts, they need high level of precision and accuracy to work with the applications. And this is another application in med device again. So here, the application involved a multi-part assembly. So we have these needles that are used in eye surgeries. So we have a needle and the cap, and they have a 60 micron tolerance. So the customer was doing this as a completely manual process. So the challenge was to improve the yield as well as the throughput. So you can think about similar applications in your side as well. Like a lot of these applications typically involve an operator looking under a microscope, doing an assembly under a tweezers. And these are low yield tasks that are not well suited for automation until now. And what we see is like they will assemble the parts or put it into a fixture and then have the automated process to do marking or oven molding and so and so. But still the manual process exists. So that's where our robot comes in with an application like here. So what they did is, they are muted up. So we have our robot, two robots, presenting the part under a LMI go-cator. So it is able to calculate the offsets in X and Y and Z axes. So in addition to being highly repeatable, our robot is able to handle a step resolution of 1 micron step size. So they are able to align in real time, so kind of like active alignment. So it's able to align the two products together and then do a precise insertion task. Enough. So one of the things I want to touch upon is working with a lot of medical device companies here and with projects like these kind of challenging ones. What we notice is the typical challenges, like they think the robot is precise, we have a feeding system, everything should be easier. But there are certain challenges. The important thing is understanding what is precision and what is accuracy. Of course, you all know the difference, but to reiterate it, so our robot is precise. Every 6-axis robot, the spec that is being published is more about the repeatability. It is not the accuracy. So in certain applications, you need repeatability. Like pick and place, you're going to the same location that you taught. So repeatability is measured like you teach a point, how often the robot how close it can get every single time. So for us, we are best in class at 5 microns. But let's say you are using an application where you are deciding a target dynamically based upon, let's say, a pallet location or so and so. That's where accuracy comes in. And every 6-axis robot, as long as they are not calibrated, they're not going to be accurate. This is not something for our robot, it's for every robot. So why it needs to be calibrated? The reason being that there are certain dimension tolerances that are not easy to control when you're assembling a robot. Basically, they are a 6-axis serial interconnected devices. So everywhere the error creeps in. So how the stiff the harmonic drives are, how stiff the motor systems are, how is the bearing structure, and how much of tolerance you have in machining. So in our case, ours is one of the rare robots where everything has been CNC machined with tight tolerance. Still, there is going to be error. And there are other robots that are mostly like with precision cast components as well. But that being said, there is going to be a different signature for each robot. So if you look into a robot, so what we do in inverse kinematics is we take the ideal version of the inverse kinematics. Basically, we expect the link offset from axis 1 to 2 would be something like 135 millimeters, and this is a nominal model. It makes inverse kinematics, the calculation, much easier to work with. So when you ask the robot to go to a certain target, it uses this model to compute what is the trajectory it has to maintain. So this works fine for every application where you are looking to do repeatable, because you teach on that robot, you expect the robot to do the same positioning, and it does perfectly well. Even though there is a difference, it works well for that because you are teaching it relatively, right? But when it comes to accuracy, it's a different thing. So that's where having a calibrated model is important. So if you see here, these values, the ideal values, is what we use in inverse kinematics, but you would see here in a calibrated model, it's slightly different than what was envisioned. And these are not just physical measurements. It's actually kind of impossible to physically measure the differences. So what we do is we take measurements using something like an optical tracker, laser trackers, and we use something like a CMM, and you get the measurements, and then you compute a model that kind of fits into this one. So in essence, it is basically like curve fitting. So these are not exact values that you would see here. For example, the value we saw here is 135, and I have here as 135.08. It's not necessarily that it is 135.08 in the actual robot. What it means is this value, by the optimization we get, is closest to the looks like an actual robot. And we also have a stiffness parameter. This doesn't have much of an impact in our case. Essentially, the stiffness is how elasticity affects the robot performance. So one thing you will notice in robots is when you're programming it, you will be mentioning the center of gravity and the payload as a first step. It's very, very important to mention that values. In our case, the control loop gains are designed conservatively. It doesn't affect much because our payload range is 0 to 500 grams. So it doesn't change much. But for bigger robots, this is a key parameter. So in our calibrated model as a service, when we try to see the performance with the stiffness parameter and without it, it didn't have much of an impact. But in general, having a calibrated robot, it increases the performance. Going back here, I can show you, like, we are looking at the repeatability at 5 micron or better than that, but if you look into the absolute accuracy, it can be as bad as 1.6 or 1.7. It varies from robot to robot, but this is what you see. Like, if you ask the robot to go to a location, these are the errors that you can get. Doesn't mean that the robot is bad, it's just that it is not calibrated for its function. So what we are trying to do with this calibration service is, so we have, our robot is one of those really small robots that could be actually implemented in a CMM for measurements. So what we will be doing here is we'll have dynamic poses generated, and then robot will move to the location, and we use a CMM to get the measurements. So once we get these measurements of these dynamic poses, then we are able to have an error optimization function, and that does the curve fitting for us, and it generates the calibrated model. Once we get the calibrated model, we will use it in the inverse kinematics, ask the robot to go to some validation poses, and we'll measure again with the CMM to see how it is performing. So this is an iterative process. Other robot manufacturers offer this service, but generally they try to stay away from it because they will say this is only needed if you are doing something like a CNC machining and so on. So in our case, we are looking to make this as a service where the robots can be calibrated, and this can be implemented in the robot's kinematic parameters by our own controller. Right now, you are able to do this with external third-party software like RoboDK. So you can get the calibrated model, and RoboDK is able to use this calibrated model and generate the targets based upon this actual version, right? So you can do that, but what we are trying to do is have this calibrated model implemented inside the robot controller itself. So for you as a user, it doesn't change anything. When you are specifying a motion to a XYZ coordinate, our robot uses a calibrated model and makes a highly accurate move to that particular location. So what we have seen with the performance with this service is, so these are the results. We did some benchmarking with 2 different robots. So we had 80 different measurements made with different poses and different orientations. And then we use our optimization function to calculate the calibrated model. And these are the results. So you can see here the first robot, the mean error was somewhere for a nominal parameter, it was about 750 microns. But after calibration, we were able to get it under 100 microns. So in general, we notice this is hovering under 100 microns. And for us, this is for general parameters. To give you an idea, it doesn't mean that the robot is, these errors, the high values that you see here, the max of 1.7 millimeters in accuracy error, which now changes to 0.195. This doesn't mean that the robot is inaccurate in everywhere in the workspace. How we measure is, there are certain configurations, especially like when you are rotating your wrist or your shoulder, that's where a lot of errors creep in, because in essence, the robot is doing inverse kinematics. As long as you stay in a similar configuration, you are better off in accuracy. But when you have configuration changes, which is inevitable with 6-axis robots, that's where you will see this observed accuracy error creep in. So it is one of those poses. For example, the high values we typically see will be in a configuration where the shoulder is flipped backwards and it is trying to reach a pose behind itself. So over there, we have parameters like stiffness of the motors affecting it and gravity as well. So there are a lot of factors affecting that. But overall, what we are noticing is we are able to bring down the absolute accuracy to the level of less than 100 microns. And this is based upon measurements done on a CMM as well as on an optical tracker. So, and this is what we will be planning to propose as a service for a lot of customers who need absolute accuracy performance. So the reason being that we have seen customers in med device specify a lot that they prefer a Cartesian system over a 6-axis robot in some applications where they need high level of accuracy, just because that it's more reliable and it's predictable. So with a high precision Cartesian system like a linear motors, you can do a compensation table. You can get an interferometer measurements and you can do a comp table, and your controller can access that value and then automatically adjust it. And that relationship is usually linear, but with 6-axis robots, it's not the case. It's not like I can say, okay, you can have a precise delta value from 0 to 100, it varies by this, but it's not the case with robot, right? So I cannot add a delta to my X value just like that. That's where we need this calibrated model. So for customers, this could be helping them to use a 6-axis robot in applications previously where they thought it is not possible to do so. So this could bring in a lot of interesting applications, feasibility for customers to use with the 6-axis robot. So you don't have to have a highly rigid Cartesian systems. You can take advantage of a 6-axis robot like ours. So what are the use cases we are looking at? So as I mentioned, so one of the thing is picking up the parts and putting it in a pallet. And what usually we do is, you know the index, the pitch values of X and Y in the rows and columns. So it's easier for you to, in a controller to say, okay, let me specify, go to index 1, which has a value of pitch and so on, so right. But with the 6-axis robot, the challenge is, like our robot, or any robot, right, we are looking at very tiny tolerances. So the problem is, customers are noticing that they are better off teaching every individual points rather than trying to have them programmatically go to a X pitch value and Y pitch value. So in those cases, having a highly accurate model of the robot could help these kind of like palletizing application, which could be used in kitting. So this is what we saw in some customers where they use Azrael feeder. The feeder is able to identify the location of the part, robot picks it, everything is fine. What happens next? So they are looking to place it into a pallet so that it could be loaded into a machine that does the automated process. That's where these kind of calibrated robots could be really helpful, provided the tolerance is needed. Another application is precise part manipulation. So this is something we got from watchmaking industry as well as in laser optics. So they have to rotate the part at a certain angle and they have to make these measurements dynamically. So they are saying like, I need to index like 55.6 degrees. So if you are using an uncalibrated robot, so it assumes it rotated 55.6 degrees, but in reality it might not be. So in your case, let's say you are doing a laser marking where you're doing evaluation and you want to rotate the parts or index it at a certain angles, a calibrated robot model would be really helpful for those applications as well. The other one would be obviously having similarities between the simulation as well as an actual robot. So you will have whatever you do in the simulation, you want to ideally push it into the field with an actual robot. So a calibrated robot version, when you're using it in simulation, it helps you to get as close as to the one. Again, I want to mention that this is not about path accuracy, this is all about static accuracy, meaning in position. So if you see a dispensing application over here, but it is not about the path accuracy over here, it's more about the static accuracy. And the other one would be, which is interesting for us as well, we have applications that are really like critical, mission critical, and so it's not easy to swap a robot. So if, let's say you want to swap a robot because the line is down, let's say something happened, a calibrated robot behaves pretty much identical, so you can easily swap a robot. Or alternatively, if you are looking to increase your throughput and duplicating the machine, right, it's much easier to work with the calibrated model, so because they behave exactly the same, you don't need to reteach the points pretty much. All things said and done, I want to focus on few things. Just because the robot is precise and you have a calibrated robot doesn't mean everything will work out itself. The key things we have to take note is using the right technique. So one of the important thing is we have seen customers, they mentioned that the robot is not precise enough or Azrael is not precise enough in locating the part and picking it up. The reason being that there are certain things that has not been taken into account. For example, it's very, very important to have a robust support and fixtures to make sure that everything is in the location, and it's also important to have the proper measurement of the robot cell. Sorry. And most importantly, what we encountered a lot is the end effectors. So you have a CAD model, you import the CAD model and you get the measurements from the CAD model, but obviously there will be changes. And also, I have seen customers use applications where they're using a vacuum end effector. They had kind of like a syringe tip that has been repurposed. It looks good, but the thing is, it's not a rigid part, it's flexible. So it brings its own uncertainty into positioning as well. So these are the important things you have to make sure that your end effector is precisely calibrated in terms of measurement. You have using robot support fixtures like kinematic stops to precisely locate the robot, and you have proper dimensioning of the entire robot cell. So that's it on my side.